This should be a quick video lesson on the first part of Chapter 8. We go into we touch a little bit on 8.3 and go into 8.4 and possibly start 8.5. So pull that stuff out of your textbook. If you haven't read through it, it might be worth reading through it before we start. All right, so on the first sound lesson, we got as far as this equation here. V equals F lambda. It's called the universal wave equation. And this is how we can talk or relate to the speed of any wave that's being transferred. The speed of a wave is equal to its frequency times its wavelength. So let's just toss an example of that out. If we have a wave that has a frequency of, let's say, 3,500 hertz, and it has a wavelength of 0.15 meters, then the speed of that wave, the speed that wave is traveling is going to be F lambda, which is 3,500 times 0.15, which is going to give us let's do the calculation. You try it, I'll try it. So I get 525 meters per second. That'd be a very fast wave if it was a sound wave. Okay, so that's how that calculation works. And of course, there are three different ways you can arrange it, depending on if you're solving for the speed, the frequency, or the wavelength. So it depends on which two values you're given. Next thing we get in Chapter 8, in this section, is a relationship between the speed of sound, the speed of a wave traveling through a solid object, which is usually seen as sound, and the linear density of that object, and also the force of tension in the object. So imagine, just for interest's sake, or just to get that sort of touch to reality, imagine a string, like a guitar string, and it's fixed at both ends, and you pluck this end, so you get this end oscillating, so it's going up and down and sending a wave along the guitar string. So at any given moment, the guitar string might look something like that. All right, so what we're going to do is we're going to talk about the density of the string, so how much matter is packed into a particular length of that string, and how hard is the tension force that's holding that string in place. You'll know if you've seen a guitar string or piano string or violin that you can tighten up the string and it changes the frequency of the sound. Well, that's because it's changing the speed. So, the first equation you get is an equation for the linear density, and that's just the mass in a particular length of string. So if we have a string that's, say, 28 centimeters long, so 0.28 meters. Sorry, that's the mass. So the string is 0.28 meters, and the mass is 4.5 grams. And what we're going to do is write in the linear density, which we write as mu, just to make things nice and confusing with the coefficient of friction. Mu equals the mass, which is 4.5 grams. Let's put it in kilograms to keep our SI units same. 0.0045 over 0.28. Again, punch that into our calculator, and we get a value of 0.016, let's round it to 1 kilograms per meter. Notice that this is different, a little bit different from density, which is would be kilograms per meter cubed or grams per centimeter cubed. So this is actually just kilograms per meter, because we don't care the actual density of the wire.
Mr. Please call 229.
We care about how much mass is within a certain length of the string, because the wave is trying to travel along the string. So this linear density is the only thing that really matters. That's that one. Now, to tie that in to the force of tension acting on the string, what we find is the speed that the wave travels down the string follows, it's actually the square root of this ratio. So the force of tension divided by the linear density. All right, so again, you plug some numbers in there. If I put 250 newtons, now let's play with 250 newtons, and the linear density, what did we just get? 0.016 kilograms per meter. Plug that number in. Yeah, plug that number in, and then take the square root of the answer to get the speed of the wave. We're going to get 124.7 meters per second. Now, I'm going to leave this as a little challenge for you. How we got those units from this equation. So you're going to break your newtons out into the base units for newtons and work out whether that actually makes sense. Okay? So that is the first chunk of this lesson. The next one, we talk about how the speed of sound, now we're actually talking about the speed of sound. Before we were just talking about the speed of a wave. Speed of sound in air varies with the temperature of the air, and this is the equation that it follows. So the equation for the speed of sound, this is the temperature in degrees Celsius. This is a base speed in meters per second. So a quick visual to explain what this equation is. It's a linear equation. So basically what you're doing is you're plotting the speed versus the temperature with an intercept of 331.4 and a slope of 0.606. All right, so that's what this equation does for you. So again, we can do some calculations. Let's imagine we're trying to find the speed of sound at normal, let's do normal room temperatures, 25 degrees Celsius. 25 degrees Celsius, we're going to say V is equal to 331.4 plus 0.606 times 25. And that, well, let's do a quick little bit of mental math here. 0.6 times 25 is 15. 0.06 times 25 would be 1.5, so 0.006, that's this chunk here, is going to be 0.15. So we're going to get 15.15 added on to 331.4, so it's going to be 346.55. Check that on your calculators and make sure I got it right. And if I didn't, post on Wasp Patterson. Okay, so that's a simple solution for this equation. And of course, this can be arranged to solve for temperature as well. I'll leave that for you algebraically. One other thing I'll toss in is you'll notice that these two equations have some common elements. So another challenge for you, another sort of extension to this process would be to try this question algebraically, given less information, not given the linear density, but say given a mass and a length. All right? Or solving backwards for something. All right, finally, one last thing on top of the temperature. Temperature equation for the speed of sound is the concept of Mach. Now, I'm sure you've heard the term Mach. It's a measure of speed. It's just another unit, essentially, but it's a unit that varies. Basically what it's saying is Mach is equal to the speed of sound in whatever situation you're dealing with. So if we're talking about the speed of sound at 0 degrees Celsius, let's come back here. 0 degrees Celsius, the speed of sound is 331.4 meters per second. That means at 0 degrees Celsius, Mach 1 is 331.4 meters per second in air. If you want to know Mach 2, then you multiply that by 2. So it's 2 times the speed of sound. And Mach 5 would be 5 times this value, 5 times 331.4. That's all that Mach is talking. Now, if you change the speed, the temperature change the speed of sound for whatever reason, then this base unit is going to be different. So Mach is going to be different. For example, if I asked you what's Mach 2 at 20 degrees Celsius, then you would say 2 times 331.4 plus 0.606 times 20. And that would give you Mach 2. Okay, next thing we're going to tackle is sound intensity, and I will build that video early next week because I want to give you some time to practice this stuff. Good luck. Have a great weekend.